that need help with next part of the project can succeed with that too. Okay? Are we good? You guys that have been gone, you know what to do to get caught up? Maybe you already did. That'd be awesome. I'd be so impressed. But you have a long weekend. How nice is that to have 2 3-day weekends in a row? You have a long weekend to get caught up. So make it happen, okay? All right. How do I want to do this? I want the computers closed for the moment. Because what I think we should start with today is some review. So please take one of these whiteboards and then pass it backwards. Take one and pass it back. Do I need one? Take one and pass it back. All right, heads up. The erasers are coming out. Amanda, only one for each table. Oh, that one kind of split. Those pieces are still usable, so pick up those pieces off the floor. So that's all that I have. You're going to have to share with one another. Pass those pieces back. Only one eraser per table, all right? Is there any more on the floor? Take one, hand them back. Take one and hand them back. Hang on to the last two. Please let me know if you need an eraser. A marker. Maybe your marker doesn't write perfectly, but as long as it writes a little bit, we'll be fine. Okay. Because we should use them until they're completely dead. And you can move up to your table. Okay. And then you can move around. Okay, are you ready? Everybody has their own whiteboard. Yeah, everybody gets their own. I said one eraser per table, one whiteboard per person, one marker per person. Because I need all your brains engaged here. No, I didn't.
No, he did say whiteboard per person.
Everybody got one?
Eraser per table.
Anybody need one? Did you match it up? We don't know. That's because you're not going to make any mistakes. Oh, then you're not going to scribble all over your board. You'll have to share a few things. Okay? That's kind of. Question number 1. Are you ready?
Wait.
Here we go. Review question number 1. Please list. Let's make it 5 kinds of energy. Please write down 5 kinds of energy. Types of energy. Five kinds of energy. Not at all. And you've got 5 out of 5. Very good. That's 5 out of 5. There's more than one way to get 5 out of 5 on this. That is 5 out of 5. Not friction. Actually, friction is a force. That's 5 out of 5? That's 5 out of 5? Sure is.
Here.
What's K stand for? B? M. 5 out of 5. 5 out of 5. A lot of A pluses here. Nicely done. Yeah, I like it. Okay, yeah, then erase it when you're done with this. Good, good, good. Did you get 5 out of 5? Mechanic units? And then A. I think mechanical. Is that 5 out of 5? Mechanical. Hey, Cassie, did I see yours? Look at that. That's good. How about you? That's 5 out of 5? Okay.
We gonna erase them now?
Yeah. What else? What else, Cassie? What happens if I flip the switch on the wall? What kind of energy did I turn off? And then what kind of energy controls the light energy? Yeah. Are you a diver? Yeah. You have a scuba? Yeah. That's a diving organization, Patty. Oh, you should be a diver. It's awesome. So fun. Both of those are dead? And you're running out, so. What? Okay. Let's see, the next question. Are you ready? Here we go. Please name the 3 parts of the law of conservation of energy. Name the 3 parts of the law of conservation of energy. You got it, Mia? I'm still here with you. Oh, no. 3 parts of the law of conservation of energy. These are not types of energy. What 3 things does the law say? No. What 3 things does the law of conservation? I kind of like it. Except, in other words, can't. I'm with it. Yeah, that's good. 3 parts of the law of conservation energy. Good, you're on the right track. Good job, Dylan. Keep going. Wait a minute. Can be changed. What about destroying them? That's okay. I understand. Can't do this or that, but can do the other? Jokes, I was right one time. Yes. Okay. Give me 2. Can't be made, created. Can't be converted. No, it cannot be. But it can be neither created nor destroyed. Nothing created. Okay, no, that's good. Cannot, can. Nothing created, nothing destroyed. We're missing part 3. Can't be destroyed. You got can't be made, but you need part 3. Uh-oh. Oh, erase transfer. Transfer and convert are the same thing.
Yeah.
Ozzy, did you get it?
Yeah.
Cannot, can. Good.
That one, right?
Yes. Yes. You got 2. What's the other one? We can't make it, and we also can't. Exactly. Yeah. Okay, are we ready for number 3?
Oh, yeah.
Number 3. Erase your boards. Let's move on. There is an equation for this chapter on the title page of the project. What is that equation? And you need to be able to tell me what each of the things represents. What is the equation on the title page of this chapter? What is the equation? What is the equation on the title of this chapter? I see a lot of people on the right track. That's it. Keep squeezing it out of your brains.
You got it, Master?
That's correct.
What is it? Is it a channel?
We're done with it.
Beauty.
That's so fine.
Hey, how about that?
That's good.
Energy equals kinetic energy plus potential.
Good job, both. Wait, that's not right.
Really?
No. That's the thing. Did you get it? Where's the equal sign? Oh, that's an equal sign. Where's the plus? Yes, perfect. What do those stand for? Oh, I already asked you that earlier. What do those stand for?
It's just easier with, yeah.
What's K? What's K? Good. Oh, I like what you did.
Yep, perfect.
Hey, Kayla, Daffy, or is it Daisy? Yeah. Iona, will you stretch your wings and fly out into the hallway for a minute? How are you doing? Perfect. You know what they stand for? Excellent. Very good.
You're welcome.
Perfect.
That's pretty cool.
Good. How about you guys? Did you get it too, or you just watching? Oh, you erased it? But you know it? Okay. Okay, next. Erase your boards. What is this, number 4? Okay. 4. What else have we been doing? We're going to do...
It'd be fun.
Let's see. I want to go... All right, I'm just going to go here. All right, on your board. I want you to draw an energy diagram, which remember is basically a rectangle. I want 3 energy diagrams on your board, 3 rectangles. They should, first energy diagram shows the energy when, let's say a pine cone is hanging from a tree branch. Pine cone hanging from a tree branch. Draw an energy diagram to represent that energy. Second energy diagram, second rectangle, shows the energy when the pine cone has fallen halfway to the ground. Third one shows the energy when it hits the ground, at that very moment that it hits the ground. When it's halfway to the ground. First one, okay, you're on the right track. You're not done yet, though. Your energy diagrams need to show the types of energy. And you need to make a key that tells what they are. 3 diagrams representing the types of energy. When a pine cone's hanging from the tree branch, when it's halfway down, and then at the moment it hits the ground. Three rectangles. And you need 2 different colors, don't you? Or you need 2 different patterns. What do these patterns represent? One of them is kinetic and the other one is, and that's why you need a key to explain which one is which. I love the tree.
Yeah.
And the cone. Oh. This one, sure. The last one should be. Now, did you make your rectangles different sizes? Or did you make them the same size? What should you have done? Why did the rectangles have to be the same size? Conservation of energy, right? We preserve the energy, conservation. 3 rectangles all the same size. What are you working on? Because this is a review for the test. If you can do this now, you got it made for the test. So you should have 3 rectangles.
Does that make sense?
got it.
You got it. You got it? Yeah.
So it's a lot easier than you think. So what you're doing is you're creating 2 keys, okay? You're it's the key, so here's the key for this, it just stops. The rectangles have to be exactly the same. I'm just gonna.
All right. So is yours something like this? If I was, one thing I didn't do that I needed to do was make a key for this, huh? What should the red one show in my key? Potential energy, and blue should be kinetic energy. The total size of the rectangle stays the same because of conservation. We can't create it, we can't destroy it, huh?
Does that make sense?
But the type of energy can change. And in this case, it changed from potential into kinetic. Now take a look at this. What if I modify this? And now I make this one like that. Am I still 50% down?
No.
Or am I probably, what do you think? Am I closer to the top of the tree or closer to the bottom?
If you have not had your picture taken, this is the last call. They will be folding by lunch. Teachers, please allow your students to come take their picture if they have not already.
So would you agree that basically I'm trying to show, let's see, potential is red, correct? And there's less red than there is blue. So is this towards the top of the tree or towards the ground? We know it's not at the halfway point, huh? So is it closer to the top or closer to the ground?
Ground.
Looking at the colors, what do you think? Is this closer to the top of the tree or closer to the ground? If it was 50-50, it would be equal, huh? But is it more kinetic or is it more potential? It's more kinetic, which means it is closer to the ground. In fact, if I was to animate this, if I had a way to animate this energy diagram, which I don't, but wouldn't it do this? We'd start it with it all red and gradually the blue would get bigger as it's falling to the ground. Is that right?
Yes.
And then it would end up all blue when it hit, huh? So could we calculate the amount of potential and kinetic anywhere along the way?
Yeah.
Like if we knew how high the tree was and we knew the height of the object, we could find out what percent it would be, huh? We could do that. Yes, sir. Okay. You need to leave your phone up here when you pick up the pads. Are we good with that? Okay. Next thing, I want to remind you of the equation for kinetic energy. Oh, it's not here. Okay. The equation for kinetic energy. Let's see, I'll just do it here where I have room. Kinetic energy equation is KE equals mgh. What does M stand for? No, not in this case. That would be ME. It would be mechanical energy. This is mass. G is gravity. H is height. So I want you to find out. Oops, I said KE. That's not correct. That's PE. I want you to find out the potential energy that was in this pine cone when it's up here in the tree. It's all potential, right? And I'm going to tell you the mass of the pine cone is, let's say 1.2 kg. Guess what? You need a calculator. What's the gravity? What number do we have to remember for gravity? Yeah, 9.8. And the height of this pine cone is going to be, let's say, 47 meters, which is pretty tall. 47 meters off the ground. That's like half a football field high. So what do you have to do? Do you have to add, subtract, divide, multiply? Do you have to square it? What do you have to do? To get this answer, what do you have to do? All you have to do is multiply those three numbers together. Huh? If you multiply those three, you should get the correct answer. So go ahead, get a calculator. It can be the calculator on your phone. I don't care.
552. Okay.
Yeah. Write down your answer on your board when you got it. Okay, Noah, thank you. Good job, Lucia. Good job. Get it, Dylan? Yes, you did. Good job, Ashley. Good job. And who else wants to show me their board? Okay, Ozzy. Okay, Abe, yes. Oh, this is slightly different. It's really close to being the same, but something happened that's a little different. So it seems to me that you should have gotten $552.72 what? If I'm measuring energy, this is joules. So I want to put J down there. Okay. All right. Now, next question. How much kinetic energy is at this position? And just so you know, kinetic energy is 1/2 mv squared.
That's kind of
And I am trying to get you to think for yourself here. Do you need to use that equation right now? Think about it. The pine cone's hanging there at the top of the tree. Its velocity is 0. So what's its kinetic energy? 0. Right? Or you can just think of it, oh, it's at the top of the tree. It's not moving. Its energy must be 0, correct? 0 what? 0 joules. Now, what's the total mechanical energy, please?
552.5.
How do you find mechanical energy? No, just add. It's simple. Take kinetic energy plus potential energy. In this case, it's really easy. You just copy down the potential energy again, don't you? Yeah, it should be 552.72. What? Are we good with that? Okay, let's go to our 50% point. We're halfway down. Please find the potential and the kinetic and the mechanical energy when the pine cone has fallen halfway to the ground. How much PE, KE, and ME when it's halfway to the ground?
Oh.
It's halfway. I made it easy for you. Halfway.
Get 276.36.
Yep. divided it up.
It's divided by 2.
No, not the
All right. So here's how this works. What does the law of conservation tell us? We cannot create energy. We cannot destroy energy, huh? So we have to take the total energy, which was mechanical, and that's the same. Mechanical energy should still be 552.72. Right? It did not change. What about on this next one? What's mechanical going to be there? It doesn't change. So whatever this was, 552.72 joules, whatever that was, it's going to be the same all the way across, isn't it? I could easily fill that in right now because I already calculated that. Doesn't change because energy is conserved. Right? Now, when it's halfway down, doesn't that mean that 50% is kinetic and 50% is potential? So all I have to do is what? Just divide by 2, right? 552.72 divided by 2, what does that give you? 276.36. I like that answer. Huh? Wait a minute, is that for potential or mechanical? What do I do with that 276.36? I do it for both of them, don't I? And that's joules, right? They're the same now because it's 50-50. That means they both have the same amount. They both have half of that total energy we started with. Was somebody's hand up?
Yeah.
Or was I just getting? Yeah, I thought I was getting distracted by a halo, but it was a hand. Please leave your phone when you go. Are we good with this? Are we clear why they're both the same answer for PE and KE? Aren't those boxes about the same size right there? Yeah? Okay. Then what about the last one? Can you finish that one for yourself? That one should be easy. You don't even have to do any math. One of them is 0, but not both. How do you do that one? There's no negative energy. Except when you're really angry. Yeah. You know it? Okay. Let's see what you got. Oh, no, you're going to write it down and show me. How much potential, how much kinetic? Think about it. What did we draw? How much potential? 0 potential because now it's on the ground. Does it have the potential of falling any further? Does it have the possibility of falling further when it's already on the ground? No. So potential must be 0. Right? Potential has to be 0. What about kinetic? No, it can't be 0 because we can't create or destroy the energy, huh? So remember, this is one little tricky point. We're talking about the very moment it hits, right? It hits, and then 2 seconds after that, that energy has been dissipated. So if we delay in our measurement at all, that 552 will drop down. And we're going to talk about what happens to that energy in a minute. But what we're talking about on this problem, at the moment it hits, it's all kinetic, right? It's the impact itself. It is the collision between the pine cone and the ground. And so that would indeed still be 552.72 joules because of conservation of energy. It's all been converted to kinetic at the moment it strikes the ground. Nicely done. Are we good with that? Let's do one more of these. Let's see. Its height was 47. Guess what? I'm going to make this be an unknown. See, I need a big question mark. And what's going to happen is we're going to have to change, we're going to redo these ones. We're going to recalculate our potential energy here, and we're going to recalculate our kinetic energy here. And now, instead of knowing this is 50-50, it's going to be something else. I'm going to have it be, oh, let's say, right. So this is, oh, come on. This can be very tricky using this stuff, huh? That's why we practice.
So is that 3070?
We don't know what this amount is anymore. But what we know is that it is, let me see, it is at 32 meters above the ground. It's, no, there's somebody there. It's fallen a little bit. It's still 32 meters above the ground. Has it fallen halfway yet? It started at 47. Has it fallen halfway? It hasn't fallen halfway yet. So we got to figure this out. So let me do this with you. Please take your calculator and put 32 divided by 47 equals, and you should get point something, 0 point something. And it should be more than 0.5, am I right? 32 divided by 47, 32 divided by 47, you should have more than 0.5. Okay? Are we okay with that? Are we doing it, Ozzy? So 32 divided by 47 equals, now take that times the total energy times the total mechanical energy. Not right now. We got to do this problem first because we're doing something new now, so I want you to participate. 32 divided by 47 gave us the percentage of the way it fell to the ground. It was still 68% above the ground. Now multiply that 0.68 times 552.72, and that gives your joules of potential energy. One more time from the beginning. How high is it in this diagram? It's 32 meters high, right? Come on back, people. Hey, guys. Hang on to that number. I'm waiting for you. Hey, guys, come on back, please. There's a lot of chatter. Mentally, a lot of people left. Amanda, Ayana, Amanda. Thank you. So let's try that again. 32 divided by 47 gives you 0.68 in a bunch, right? That means it is 68% of the way above the ground. And that means it still has 68% of the potential energy in it. So take that 0.68 times how much total energy did we have before? 5.552.72. Multiply, I get 376.32. And that would be my potential energy. What was it, 376.32?
36.31.
Okay, either way, doesn't matter. So how do I find my kinetic energy now?
3 by 5. Yeah,
Just make sure you get a positive answer.
okay.
How do I find kinetic?
Yeah.
Well, if this much is potential and this is the total, the rest has to be kinetic, huh? So don't you just subtract to find the kinetic energy?
Now can I go?
Actually, somebody asked before you.
What?
Yeah, somebody asked before you, and I made them wait too.
Can he go?
I want to finish this problem first, okay? You already do it?
I finished it.
Okay, I want you to participate.
I am.
Because this is a tricky thing here we're doing now. We're making it a little tougher by not always having 50%. So you have to figure out what percent is it? And in this case, it was 68%, huh? Because we took 32 divided by 47, that gave us 0.68, which is the percentage, 68%. Multiply that by 552, we get this as our 68% of the original energy. How do we figure out the kinetic energy? Remember, potential plus kinetic makes mechanical, correct?
Yes.
So you have to figure out how much would it take to make that mechanical. To do that, you just subtract, and did you get 216.4?
176.41.
What?
176.41.
Did I make a mistake? 552.72 minus 376. I bet I put in the wrong number. And I get 176.4.
Yeah,
Yeah.
I got that.
Are we okay on how I calculated that? Is good? I want you to try one more on your own. Now, it has fallen past the halfway point, so it's mostly kinetic. And we're going to say that now it has fallen, it is still, let's call it 12 meters above the ground. So we're going to recalculate, do that whole series of steps over again, but now we're going to say it's 12 meters above the ground. We got to find out our potential and our kinetic energy, but it's 12 meters above the ground. Do the math.
And then we multiply.
How did we do that? We got to take the same steps that we just did.
I did too.
I got up to I got the percentage.
What's the first thing you do to find the percentage?
You multiply, or no, you divide.
Divide.
By 47.
12 divided by the total of 47.
I got.
We don't need this 32 anymore. I'm just going to get rid of it. That was the previous problem. 12 divided by 47 is your first step, right?
Oh, and then we multiply 52.7.
I got 25.5%.
I got the answer.
And then what do you do with that 25.5%? Multiply by the total mechanical energy, huh? And is that potential or is that kinetic?
Kinetic, yeah.
No.
Oh,
That's potential. Because we're calculating it using the height. Let me see that again there, Ayana.
I got
You got the same thing I just wrote?
No, wait.
Now, how do we find, last thing we have to do is find the kinetic. How do I do that? I just go 552, take away 141, huh?
Yeah.
Whatever's left is going to be your kinetic. 552.72 minus, what was it? 141? What was it? 141 point what? 0.12? Thank you. That'll do. And I get 411.6. Is that what you're getting? I hope. Okay, please erase your boards and pass them to the front of the room. Please pass the box to the back of the room. Put the erasers and the markers in there. Pass this backwards. Pass the boards forwards. And then get your computer out and fire up the project. It's not. They might say that, but it's up to me. Yes, thank you for waiting.
Erase it. Whose is that? So whoever that is, erase it before you set it back up. Erase it before you set it back up. Erase it.
My phone, sir. Thank you. Hey, Dylan, you can get it back from eBay next week. Weightlifting. What about yours?
Oh, mine.
Yeah, they're more heavy than you would think.
Why?
They're dense. Thanks, guys. The box is on the way back. It's coming up. The pens, markers, and erasers go in that box.
Guys, go get that marker, whoever that is.
Okay, so please get out your computers and open up the project. Open up the project.
Yeah, that is true. Or like anything but. Anything but. Every single mountain has. Is that the name of the policies at Tahoe?
Okay, I see some of you are going straight to page 9. Very good.
And they
So,
all right, here we go.
Page 9.
9. 8.
Okay. So.
Don't.
So awkward. Sorry. It's all the charge. Okay. So, can I get your attention, please? Here's page 9, right? Here's the big idea. During a fall, potential energy gets transformed to kinetic energy. On the next page, we're going to investigate this next question. What happens to the energy during a bounce? What I want you to do here is notice, first of all, the key. E stands for PE, KE, E, we read this, look at it, E sub T. You see that? This is a T down below there. So the way you read it is E sub T. And in this case, that stands for the total energy, which was ME. The mechanical energy, huh? What else do we have? M stands for G, H, and V is. Now what I want you to do is I want you to choose a color and put a box on top of the PE. I want you to choose another color and put a box on top of the KE. Your choice of what colors to use to represent PE and KE. But update your key right now. So you're going to make a square.
Why can't we just use a pencil and color it in?
Because we're doing it in digital.
No, like the pencil on the thing.
Oh, you can color it in if you want. I prefer to make a box because it looks so much more neat to me.
It doesn't.
Oh shoot.
If you zoom in, it works quite well to draw a box and put it on top of the box. And then you just change the color by using the properties. So complete the key first of all, whichever color you want to use. One for potential, one for kinetic. And that takes care of instruction number 1 at the top, I think. What did that say? Number 1, choose a symbol or color to represent PE and KE and complete the key. Number 2, use your symbols to show the PE and KE at the 3 positions in the diagram below. Position 1, remember that there is no kinetic energy here before the ball is dropped. Position 2, while the ball is falling. Remember that there are both kinetic and potential here while the ball is falling. Position 3, at the moment the ball hits the ground, remember that there is no potential energy here when the ball is on the ground. You're going to fill in those 3 boxes for yourself using whatever symbols you made in the key. So I would, yeah. Did you leave your phone, right? So if I was doing it, I'd be using orange and green. Kind of reddish orange. Kind of tennis ball green. Whatever symbols you chose, these 3 diagrams need to match, right? So go ahead and fill in the rest of those diagrams and you'll be done with page 9. You guys are working awesomely. Look at go. I'm impressed. Natasha, you asking? Drop your phone off, please. What you need to do?
Fill in the things.
Yeah, fill in the energy diagrams to represent the amount of energy at the very top, halfway down, and at the bottom.
Hey, can we try saving this right now? Yeah, fine, save that. You know how to do it? But it hasn't been doing it? Where have you been saving it? Where is this? It's just this PC. This is, that's weird. You're saving it in downloads? Is that what you want? Just save it in the downloads? Okay.
And before you leave, let's open it and double check towards the end of class. Okay, are you guys done with page 9? Are we okay? We ready for page 10? Yep. You need more time on page 9? Page 10 then? Okay, when we drop a ball, like we did in the lab the other day, we had these energy transformations occur, correct? Went from potential to kinetic. But in this diagram, it just stops when it hits the ground. Is that what actually happens when we drop a ball? It bounces back up, huh? So what happens to the energy when it bounces? Well, wait a minute. Does it bounce to the same height it started from? It does not bounce as high as it started from. Does that mean that the energy was destroyed? No. We can't destroy the energy, can we? So that energy had to be converted to some different kinds of energy. And that energy was lost from the ball. Was it lost from the universe? No, that energy is still in the universe even today. That energy is still present. It's not in the ball anymore, though, is it? It was basically lost to the air around the ball, huh? And then it kind of was dissipated. You know that word dissipated? Like, let's say I have $100 and I give everybody $1, but I give it to you in pennies. And then you have to give those pennies away to all the little kids at the elementary school or something. Was the money dissipated? It got thinner and thinner and became less and less, and it got more spread out, didn't it? Right? That's what I mean by the energy is dissipated. It spreads out thinner and thinner, further and further away through the air. Does that make sense? Is it destroyed? No, it's just transferred. Is it useful to us anymore when it's dissipated? No, we can't make use of it anymore, can we? But it's still there. Right? So let's look at page 10. And page 10 is going to start on the left. Let's read this together. Study the diagram by following the numbers. They're over here next to each energy diagram box. Study the diagram by following the numbers. They go down on the left side, and then they bounce back up on the right. Pay close attention to the different kinds of energy transformations, especially during the bounce. Also notice the amount of total energy as shown by the size of the boxes. So let's start by once again showing the potential and kinetic energy during the fall. How much of it should be potential at the beginning? What percent? 100% potential. What percent potential halfway down? 50%. What percent potential at the bottom? 0. So you're just going to repeat yourself right here. Go ahead and do that. These first 3 will look the same as page 9. Okay? Go ahead and do the potential and kinetic energy conversions during the fall. You right click on it and then you hit properties.
Click on the circle.
So you should end up with something like this. Is that okay? Did I do it right? It doesn't really matter whether it's on the bottom or the top. Go ahead and do all three of those boxes. You're working on it? Oh, I see. You look so relaxed.
Yeah, wearing your
No, every teacher tries to.
That's Canadian.
Looks good, you guys. I hope you have one color at the top, two colors in the middle, and a different color at the bottom, right? Yeah. Okay. Oh, actually, let's wait a minute, because this is the tricky part. Come back, everybody. Now, this is going to get a little bit tricky. It's going to get a little bit more complicated. So, look what happens to the size of the box here. Can you see that this is the energy when it hits the ground? This is the energy when it begins to bounce back up. So think of this in slow motion. The ball has fallen to the ground, and the first box is at the second that it hits. And this box is the second that it bounces back up. The beginning of the bounce is here. Is this box the same size as that box?
No.
No. So what happened to the energy? It got smaller because some of it was converted or transferred into other types of energy, huh? Can you see that there's three types of energy that it's showing you that it got converted to? What are those three types of energy? Elastic energy, sound energy, thermal energy. When the ball hits the ground, can you hear it? That's because some of its energy was used to make that sound. It's really hard to measure, but you could measure the heat from the impact. And of course, the faster it's going, the more heat there would be, which is one reason that asteroid that hit the Earth and killed the dinosaurs was so devastating, because it was going so fast, like 20,000 miles an hour, and it hits the Earth, and that's going to create a lot of heat, and there's going to be a big blast wave from that impact. Finally, there's elastic energy, and the amount of elastic energy depends on the type of ball, and that's when the ball went from being round to kind of getting squeezed a little bit and then bounced back. Like if it was a rock, there would be almost no elastic energy, huh? So some materials have more elastic energy in them than others. So this is what we need to do. First of all, since the ball is bouncing back up, it is actually moving, and this is now all kinetic energy still. When it bounces back up, it's still moving, but it's moving upward, isn't it? Its velocity changed because it changed direction. So this is still kinetic energy. So I'm using the same color to represent that. But now I need to pick 3 more colors to represent those 3 other kinds of energy. The elastic, the sound, and the thermal. So let's see. Oh, I know what I'm going to do. I'm just going to copy paste what I already had. And I'm going to change its properties by making it go, oh, I think I'm going to make one of them this kind of fuchsia color. And I'm going to make it fit this box right here. And then I'm going to copy and paste that one, and I'm going to change its properties. So it's kind of this brick color. And then I'm going to copy and paste again and change it one more time. Let's see, what am I going to go with? What do I have? Oh, I've got a blue. How about that? That'll be the thermal energy. So this is all the energy that was subtracted from the total energy. If I took these 3 types of energy, added it to the kinetic, I should get the same total that I started with. It's not mechanical energy though anymore, is it? Mechanical is only kinetic and potential. So I want you to fill in these colors. Then I want you to fill in these 2 blanks. This energy is what from the ball? Does the ball still have it? That could work. There's different words you could use to fill in. Since it is what to the air? Does the ball still have that energy, that thermal, elastic, and sound energy? Or did it lose it? Yeah. But where did that energy go? Or into the air. It could have gone into the ground or into the air. Yeah. What happened to the energy? Did the ball keep it or did it lose it?
It lost it.
Yeah. Because the energy was, we say that energy can do? It cannot be created, it cannot be destroyed, but it can be converted or it can be transferred. So when we say converted, it's a little bit different than saying transferred. It's, let me see, will you help me out, Cassie? Take those. Did I convert or transfer those keys when I handed them to her? I transferred them, huh? If I converted them, then I would, like, I don't know, take a hammer to them or melt them. That would convert them, wouldn't it? So is energy converted or is energy transferred in this example? It was given away from one thing and taken up by another thing. That was a transfer. The conversion is when the kinetic turns into potential. That's converting energy. Transfer energy is when you move it from one object to another. So this energy is, okay, this energy is taken from the ball. This energy is lost from the ball. Since it is transferred or given to the air. Does that make sense to you? Let's see your fuel gauge. This means it makes total sense. This means you have no clue what it's doing. Show me your fuel gauge. What do we got? Total sense. Okay, it was all transferred. And then we have one more diagram to do. Am I right? Oh, 2 more. Oh, okay, I see what's happening. We've got a little, this one's a little more complex. So. Look at this one. Is it halfway back like it was before? Or is it more than halfway? It's bounced more than halfway back, hasn't it? You can tell because the halfway mark is right here at the 50%, isn't it? Pretty close to 50% at any rate. So this one's more than halfway back, which means I need to once again use my potential and kinetic colors, but it's a little higher, so it's not 50-50 anymore. It's more potential than it is kinetic. Here it is at the top of the bounce. What kind of energy would that be when it reaches the top of the bounce? Just at the moment it gets to the top and it's almost ready to start falling again. It would all be what? Potential. So shouldn't this one, number 7, be all potential at the top of the bounce? And number 6 is almost to the top of the bounce, so it's mostly potential. Maybe not 100% potential, but mostly potential. And the rest is kinetic. It's almost to the top, but not quite. Ozzy, let's stay focused on this. So it shouldn't be 50-50 at number 6. It should be mostly potential. A little bit of kinetic. It's almost to the top. When it gets to the top of the bounce, it's all potential again. The last thing that we need to do with the diagrams is make a key. So you need to make a key up here that shows what? 5 different colors, I think, huh? That was on the first diagram. This is a different one. We're using some things on this one that were not on the first one. So please make a key with the 5 types of energy. You don't have to include all the symbols anymore. You don't have to tell me what KE stands for, but you need to show me what color you used for KE and PE and thermal energy and sound energy and elastic energy. So show the 5 types of energy in your key, please.
Could you just go down for a little bit?
So we're making a key up here in this box with the 5 different kinds of energy. You don't have to include ET anymore. watching your age, just the 5 colors boxes are used.
Ms. Farley?
Yeah. Yeah, but I want all 5 colors, right?
Oh.
Yeah, what color? Yeah, because we filled in different colors to represent these 3 types of energy down here, right?
Oh, gotcha.
So what I'm saying is you need a color for potential in your key. You need to show me what color you used for kinetic, and also you need to show me what you used for elastic, sound, and thermal. I used fuchsia, brick, and blue for those 3 things, huh?
Can you sing chicken?
Oh, I can't do that right now. You're gonna have to get me at lunch.
Oh, all right.
Okay. So let me tell you what's going on. I think you're aware that class is almost over, huh? Gentlemen, ladies. So we're actually not done with this page. So we have to come back to page 9 on Monday. Is that when I see you again? Monday?
Hold on, no.
Yeah.
Because tomorrow you would have been Friday.
No, yeah.
Yeah, we see him on
So,
Monday.
so even though it's Veterans Day, are we gonna, this Monday?
I think they plan, well, if it's a holiday,
It's
they
a holiday,
plan
it
it.
starts over.
Yeah. So I should see you on Monday. And on Monday, we're gonna do some math on this same page. Today, we just did the diagram section of it. We still need to do the math part. So let's just remember to come back to that together on Monday. I don't want you to have to figure out how to do that by yourself. So let's look at page 11. What does it say on mine that it doesn't say on yours?
Highlight.
Yeah, I want you to highlight the important text. And remember, that should basically be at least 1 section highlighted for each paragraph, right? I'm describing your homework right now, your spooky homework. Then you fill in the blanks down here, don't you? Then I want you to move on and do page 12 by yourself. So please look up here at the screen so you can tell what you're going to do on page 12. Here's the ball falling and bouncing back, right? Can you see that it got squeezed when it hit the ground? What kind of energy squeezed it? Elastic energy, uh-huh. Here's some reading. What are you going to do in this reading part?
Highlight.
Yeah, you're going to highlight that, but here's your instructions, and this is on yours too. It says, add labels and arrows to the diagram that show the energy transformations described below. So you're going to need to write some things down, like potential energy, elastic energy, sound energy, kinetic energy, and you show arrows what they're doing. Like, what does the elastic energy do? Does it move back up, or does it move away from the ball? It's lost from the ball, isn't it? It's transferred to the air. So for this one, you're going to read these descriptions. Let's look at number 1. Stage 1. Energy is lost a really, really small amount due to air resistance. Oh, I haven't talked about that yet, have I? But I think some of you have been thinking about it. As the ball falls through the air, it loses a little energy because of friction with the air molecules, which is the same thing that causes a meteor to burn up because it's moving so fast. When it hits air molecules, it heats up and burns up. So how would you show that? Well, I might grab a pencil And I might show a little wavy arrow as best I can. Kind of hard. There's an arrow showing energy lost to air resistance. Does that make sense? When the ball collides with the air molecules, both the ball and the air are made a little warmer. So I've finished number one now. Have I described, excuse me, have I diagrammed what they described? Does that make sense what I want you to do? I want you to take whatever they describe in stage one and add it to the diagram. Same thing for stages 2, 3, and 4. So you have those 2 pages to work on for homework tonight, right? Page 11, page 12. Don't forget to highlight the important stuff as you're reading. And thanks for being here, Mia. That's all we have for now. Have a good weekend.